All right, everyone, now that you've taken some time to go over this worksheet as a review of the work we did yesterday, I'd like to go over it with you. So the left side here is similar to some of the information we went over yesterday, but includes a little more information as far as these exact angles. They're all about 109.5, and you don't need to know that they're exactly these amounts, but they will become a little bit less just because of those lone pairs taking up a little bit more space. And just another example with ozone here and the exact angle that it makes, which is less than a 120, but there's still 3 electron bonding regions. So what is electron region for number 1? I would just say that it's any area or groups of electrons, whether it's a bonding pair or 2 pairs, whether it's a double bond, that'd be a region, even, or a triple bond, that's a region, or a lone pair, all those things. A lone pair electron region would just be where when there's a lone pair. And a bonding electron region for number 3, I would say where you have a single, double, or a triple bond. So it's a group of 2, 4, or 6 electrons. As we look at number 4 here, what determines what types of how many electron regions? Between 105 and 109, we would have 4 regions. If it's approximately 120, that'd have 3. Reminder, this 120 is a way to get those 3 regions that are around the central atom as far away from each other as possible. And approximately 180 would have 2 electron regions. I know here that I've given you different ones, and the reasons why I've given you different ones, because the ones that are on your sheet, or were originally on here, like you see here, are actually repeats of what you've already done on your Lewis structure sheet. So I'm giving you some new ones. So if we do nitrogen, or the nitrite ion actually, you would have 5 from the nitrogen, 6 from each of the oxygens, for a total of 5 plus 12, which gives us 17, plus this minus 1 here, so that's 18. So in this situation, the only way to get 18 is with 1 single bond and 1 double bond. And the Lewis structure would look like this. And we put it in brackets and with a minus 1 charge. The PCl5, there's 5 from the phosphorus, 7 from each of the chlorines, so that gives us a 26 total. So I'd put the chlorines out here with single bonds, and it works for single bonds and 3 lone pairs around each of the chlorines. I'm not going to draw them around the rest of them, but then there'll also be 1 lone pair around the phosphorus for a total of 26. And then CBr4 also works with all single bonds. We'd have a bromine on the ends of each of these with 3 lone pairs at the end of each one. So I'm not drawing the bromines. There'll be bromines here, single bonds between the carbon and bromines for a total of 28 electrons. Actually 32 electrons, sorry. There's 7 for each of the bromines. 7 times 4 is 28, plus 4 more for the carbon. That's 32 total. And when I count all these up, there'd be 8 around each bromine for a total of 32 when I was done. So that's that one. Number 6 is a good question, talking about the bent shape. So they're saying that both of them, actually they're not saying that they're both bent, they're just trying to get you to figure out which one would have a bond angle of about 119. So when I figure out the Lewis structure for SO2 and SH2, SO2 would be like this, looking a lot like NO2 minus above, and SH2 would look like this. So the question is, which one of them would be about 119? And the answer is this one. And the reason why is because around this sulfur there's 3 electron regions, which makes it around 120 for the angle. But since there's a lone pair here, that becomes a little bit less than 120, but not much less. This one, there's 4 regions around it, so that's going to be more like 109 degrees. And like you see on the left side of your page there, in reality, since there's 2 lone pairs, it's actually exactly be 104.5 degrees, but definitely would not be 119. It would definitely be more around 109. So if I move down from there, Number 7 says 3 molecules have a total of 4 electron regions, bond angle slightly different, lone pairs, and that would tell us that the lone pairs do take up more space because as we add lone pairs, it kind of pushes those angles together. So for instance, with 4 regions and 4 of them bonding, and we have 109.5, 4 regions but only 3 of them are bonding, and 1 lone pair, it pushes those angles close together, being 106.5 instead. So it takes up more space. That's the proof that they're talking about there, looking at the lone pairs and bonding pairs that exist. Now if you turn the page, the goal of this sheet, or this part of the sheet, is to show that even with a larger molecule, we get the angles will still hold true. So they're showing this structure, this Lewis structure. Well, it's not a Lewis structure because they don't show the lone pairs on everything, like this oxygen. A couple of those oxygens don't have their lone pairs shown, which I will just show you what I mean by that. So like this would have 2 lone pairs on this oxygen. But this Lewis structure is on paper, and even though it's on paper, in reality this big molecule would be 3-dimensional and the angles would still hold true. So what I mean by that is if I look at this nitrogen, it has 1, 2, 3, 4 regions of electrons. And we're just looking at, based on the regions of electrons, what angle 109, 120, or 180 would be the approximate bond angle. And as we saw in the front, if there's 4 regions, it'd be about 109, 3 regions about 120, and 2 regions about 180. So if I look at this nitrogen, even though there's 3 bonding in 1 lone pair, there's still 4 regions, so that'd be about 109. If I look at this carbon, there's 4 regions, so it's about 109. If I look at this carbon, like it says, there's 120 because there's 3 regions. Even though this is a double bond, that counts as 1 group of electrons that will repel these other 2 regions. Same thing here. This will be 120 if I look at that carbon. There's 3 regions around it. So just pointing out specific atoms. Same thing here. If I look at this, there's 4 regions around this carbon. That would make it a 109. If I look at this nitrogen, there's 4 regions, 3 bonding, 1 lone pair, but 4 total regions, 109. If I look at this carbon, 2 regions, a single and a triple bond, so that would be 180 around that one. So this triple bond counts as 1 region, and same thing here, 3 regions, so 120. So yes, I know there's degree signs on all of these, but just looking for the approximate what you think it would be. So even though it's a big molecule, and even huge molecules like DNA and penicillin and different like insulin, hemoglobin, huge molecules, caffeine, these angles will still hold true, even though when we draw them like this, they look like they're flat on paper. In reality, they would have these angles 3-dimensionally. So that's it for this worksheet.